Yep, looks good.
Okay, so yeah, so today I thought I would talk about on the interplay between optimization and machine learning and the role of sensitivities. So it seems a bit broad, especially when you say interplay between optimization and machine learning, but the main focus here is the role of sensitivities. And so when we talk about machine learning for optimization, so there are several complex decision-making problems which can be formulated as optimization problems. And in order to handle the complexity, say for example, due to the curse of dimensionality or the computational complexity, we could use function approximators to approximate the complicated bits. Right. So this is something that has been quite popular recently with the developments in deep learning, how to exploit machine learning for optimal decision making algorithms. On the other hand, we have optimization for machine learning. So we all know that machine learning involves training models, and this means that we need to find the, the best parameters that maximizes some kind of a utility function. And this means that optimization is at the heart of machine learning, right? It always involves solving optimization problems. And when we talk about sensitivities, it's when you solve an optimization problem, when you have a solution to the optimization problem, given some conditions, instead of or just giving the optimal solution, we can also say a little bit more about how the solution changes when the data changes. So this is commonly studied under the context of parametric sensitivity or parametric optimization problems. And in this talk, I would like to say a little bit more about what is the role of this parametric sensitivity. How can we use the concepts from parametric sensitivity in this interplay between optimization and machine learning? So let's start with the first case, which is using machine learning to approximate decision-making problems. So the goal here is to have some kind of a optimal policy that tells us what decisions to take depending on the current state of the system. For example, if we want to use model predictive control, then solving the optimization problem repeatedly at every time sample and implementing the first sample on the system implicitly gives us this optimal policy. And instead of solving the optimization problem directly, we would like to approximate the policy function in order to use some kind of a approximate policy that we can then use online for evaluating the decisions based on the current state of the system. So let's focus just on the MPC part. And here we have a standard MPC problem in its generic format. So we have some cost function that we want to minimize over a finite prediction horizon. We have the system equations. We have some path constraints, some terminal constraint, and also the initial condition that tells us what is the current state of the system. And typically, we want to solve this repeatedly in order to compute the optimal trajectory and implement only the first sample on the system. And this implicitly gives us the control policy, which I denote by MPC. Right? And there are several reasons why you may not want to do this. For example, you want to solve this in a much faster sampling time, or want to implement it in memory resource or memory efficient platforms like for embedded control applications. And you may not want to solve the optimization problem at each sample time. So then what we can do is we can try to approximate this MPC policy and try to make a function approximator that can replace the MPC that we traditionally use. So this is something, an idea that dates back to probably even older than 1989, but this was quite common in the computer science literature where they called it comparison learning. And the idea here is to mimic human experts. Right? So this kind of expert-assisted supervised learning was popular in these kind of games and computer science domain. And But it's not just the human experts that we can mimic. Of course, we can also mimic optimization problems or control policies. And in the context of MPC, this idea also dates back to 95 with the work of Parisini and Zoppoli in their Automatica paper, where they presented a neural MPC. But this did not gain a lot of momentum back in the mid 90s for several reasons, I guess. But with the recent surge of interest in deep learning, this idea has gained enormous popularity. And just in the past couple of years, you would see several research groups using this idea of approximate MPC, where the MPC policy is approximated using deep learning methods. And the general framework of this approximate MPC is as follows, where you sample the state space to generate several discrete realizations of your states, xi, let's say, and you solve the optimization problem offline for each of these state realization in order to obtain the corresponding optimal input. Thereby, you get this uh, MPC policy. Now you have a training data set that is given by this states and their corresponding control input. And using this training data set, we want to train a parametric function that is parameterized by some parameters theta. Okay, and this is just a standard learning problem. And then once we have the approximate policy, we can then use this in place of the MPC function. So this is the standard MPC, approximate MPC framework, and there are several different variants of this that have been that different people have been working on. I'm sure some of you guys have also been looking into these kind of approaches, right? So um, and one of the fundamental bottlenecks of this approach is that training is expensive. Because in order to generate the training data, we need to sample the state space, and for each sample, we need to solve the optimization problem offline. And for higher dimensional systems, the number of samples that you need in order to approximate the MPC policy increases exponentially. And this means that the computational resources that are needed for training, for generating the training data is very high. And to further add on to this complexity, if there are any changes in the model parameters, or if there are any changes in the cost function, say for example, you're changing the tuning or the weights of the MPC problem, then you have to generate all this training data all over again and retrain the MPC policy. Right. So then one of the open challenges here is how can we address the issue of generating training data? If we look into the machine learning community of how some of these challenges are handled, there is this concept known as data augmentation that is used in deep learning. And this is used especially when there's a lot of in a lot of image classification problems, right? So the idea here is to artificially increase the number of training samples using the training samples that we already have, and we want to do this by by using computationally inexpensive transformations. Typically, in image classification problems, these are like photometric or geometric transformations. Say, for example, if you have 8 different images that you want to use for training, then what you can do is you can change the color, the brightness, the contrast, the white balance, and all such photometric transformations to generate additional data points, right? Or you could use some kind of geometric transformations where you crop the image, you rotate the image, and you move the image. And so you have these kind of different transformations that you could use in order to artificially generate several data points that you can then use to train your function approximately. But the problem is we cannot use these kind of data augmentation techniques that are commonly used in machine learning for our problem, which is for policy approximation. Right? So then the idea is, okay, what can we do in order to use some kind of data augmentation technique for policy approximation? Are there any computationally inexpensive transformations that we could use in order to generate a rich training data without having to solve several optimization problems offline. So here's where the sensitivity comes into the picture. So we can exploit the parametric sensitivity of the optimization problem in order to do this. So just a very brief introduction to what these parametric sensitivities are. So consider we have some kind of a parametric optimization problem parameterized by these t, right? So we want to then solve this optimization problem for a given value t. And then once we get the solution, the idea here is to say that instead of just getting the optimal solution W star, can we also say something more about this optimal solution of how the solution would change when the parameter P changes by some small amount. So if we have some conditions, such as some constraint qualification, some second order sufficient condition, and strict complementarity, then turns out we can actually say this nicely, right? So if we have a solution that we solve, say, for example, for a given parameter P naught, and we have a corresponding optimal solution, and given these assumptions that if some conditions are satisfied, then we can say that there exists a unique, continuous, and differentiable solution manifold that is given by this orange curve here that tells you what will be the optimal solution for different values of the parameter P, right? And the idea of using parametric sensitivities is that if I have a solution for a given parameter P naught, then I can just linearize this solution manifold and then approximate what the solution would be for different values of P, right? For example, P naught plus or minus delta P, then I can then easily approximate the solution from this tangential approximation. So this is typically known as a tangential approximator, which is in the simplest form of sensitivity updates. So if I have a solution for a given parameter value P, then if I want to find out how the solution would change for P plus delta P, then I only need to find this change for this change in the parameter, right? And I can get this change in the solution by simply solving a system of linear equations. And here we have the M and the N, which are nothing but the KKT matrices that you get from the NLP problem. So it's not that you have to compute this, because this you can obtain almost for free from when you have solved the optimization problem for a given value naught, right? So then we can use this tangential approximator to easily approximate how the solution would change when the parameter changes by a small value P plus minus delta P. So this is the idea that we will then use to generate additional data points. So in the problem of policy approximation, we sample the state space, right? So we get one sample and we solve the optimization problem for this particular discrete sample of the states. Let's call it xi. And when I solve this optimization problem, I would get the corresponding optimal input, which is one data point, right, for the training data set. Now what I can do is, once I solve this optimization problem, I can now get infinitely many number of optimal training data points in the neighborhood of this one sample xi, right, in order to generate additional data points. So once I solve the optimization problem for xi, I can then get several data points in the neighborhood of xi to augment my training data set. So this is the sensitivity-based data augmentation that we can use in order to augment our training data set with several data points without having to solve a lot of optimization problems offline. So here is a simple example. So here I use a benchmark CSTR process that is also used in this paper, which also deals with approximate Mpc. So here I have two states for the CSTR, which is the concentration and the temperature. And I want to say use some kind of sampling approach, and I've chosen a grid-based sampling approach here. And I want to have a the width of this grid sampling to be fine, such that I want the data points in all these points that are marked in black points. But instead of solving the optimization problem at each and every single data point in order to generate this training data set, what I can do is instead I can sample the state space more sparsely and solve the optimization problem for the data points that are only marked by these red circles, right? And once I have the solution for these red circles, I can then use parametric sensitivity in order to get what will be the optimal solution for the points that are in the neighborhood of this red sample. Now I have gotten a training data set for all these data points without having to solve the optimization problem at all these data points. So in this particular example, I generated 6,968 data samples, out of which I only solved 268 optimization problems, and the remaining 6,700 samples I obtained by using a sensitivity update. And when I use this data set to train an MPC or to approximate the MPC policy, then the closed loop solution by using the approximate policy and comparing it with the full MPC policy, we see that we get very similar performance, meaning that we're able to approximate quite nicely despite a huge significant part of the training data comes from the sensitivity update. And when we look at the CPU time for generating the training data set, we again see that the CPU time for generating the sensitivity update is significantly lower than when we have to solve the full NLP. So here is another example where I used it on the building climate control problem. And again, here I have 6,900 data samples to train the MPC problem, out of which I only solved 330 optimization problems, and the remaining 6,600 samples I generate using a sensitivity update. Okay, so that's machine learning for optimization and how we can use parametric sensitivities to generate training data to approximate the policy function. So if we go to the other direction where we use optimization for machine learning, and here we will see where we can use these ideas of sensitivity in this paradigm. So if we consider any kind of a model fitting or a statistical learning problem, we have a training data set with some features denoted by U and the labels denoted by Y. And we want to fit a parametric architecture parameterized by these parameters. So this could be, for example, a neural network or whatever, right? Or it could also be a given functional form that you have. And the idea of the learning problem here is to minimize some kind of a loss function, and also you may also have some regularization term in order to find the best parameters that would give a very good predictive capability of this parametric function. So when we have large data sets, or if we have a large number of features, then this could result in a large scale optimization problem. And in order to parallelize these kind of optimization problems, we could use the framework of distributed optimization, where we decompose this optimization problem into several smaller subproblems, and then we use several smaller worker nodes in order to train models in a distributed way. And then we use a central coordinator in order to coordinate these different nodes in order to generate a global statistical model. So there are different ways of decomposing it. Either you can decompose across the data set, and in this case, the distributed optimization problem becomes a consensus problem, or you could also decompose across features, and in this case, the distributed optimization problem is formulated as an optimal exchange problem. And for example, if when you have some kind of a problem where you're generating training data sets in remote locations, then you may not want to share the data across different locations, say because of the cost of communication or the data privacy issues. So then you could use decomposition across data set. Or alternatively, if you have, say, for example, a clinical trial, right, and you have one clinical trial that studies the effect of a given drug say, blood glucose, and you have another clinical trial that studies the effect of physical activity on blood glucose, and then you can try to combine data from these different clinical trials looking at different features, and then develop a global model, right? So that's decomposition across features. So in either case, you can formulate it as a distributed optimization problem, which you can then solve using distributed optimization methods like the ADMM, which is the alternating directions method of multipliers. So let's focus on the consensus problem, right? So I'm just focusing on the problem where I am splitting the training data into n chunks. And the other problem, which is decomposition across features, is not very different from this one. And in terms of the methods that I'm going to show, it's going to be the same. Right? So here I have split the data chunks into n data chunks, and the learning problem can equivalently be stated something like this, right? And the parameters that I want to fit are the same across all the different data chunks. This is because I want to find a single global model. But in order to be able to decompose this, I introduce local copy of this parameters. I call it xi, right? So now I have the same problem where I have xi and the corresponding data chunk di, and I add this additional constraint saying that this constraint, which is known as the consensus constraint, saying that xi must all be the same for all the local subproblems, right? That means in the end, the different subproblems must all agree to the same value of the model parameters. So we can then solve this using ADMM. So we can write the augmented Lagrangian of this function by relaxing this coupling constraint. So we have the Lagrange multiplier for this coupling constraint, and we add this additional quadratic penalty term that penalizes the constraint violations between the different subproblems. So the ADMM iterations for these for this problem is given as follows. You have the subproblems, the n subproblems, where you want to minimize the local objective, and you have the constraint, the consensus constraint for that local problem and its corresponding quadratic penalty term. Okay? And here you have the terms lambda I and x0, which are not the decision variables of this local subproblem. So then what you do is you fix these values with some value. You start with some initial guess, and then you fix it with the value from the previous iteration, and then you solve the optimization problem to find out what is the optimal xi for this given values of x0 and lambda I. And then once you have the updated solution for xi for all the local subproblems, you then update the value for the central collector x0, where you have this regularization term and the same constraints, right, which are also now seen with, or which are minimized with respect to x0 by fixing xi from the current iteration. And once you have x0, the updated x0, you can then update the Lagrange multipliers as well by using the new values of xi and x0. So this is solved iteratively in the sense that I fix x0 and lambda I, solve for xi, fix lambda I and x0 and solve for x0, and then fix xi and x0 and solve for or update lambda I. So then once I do this, I have to go back and resolve the optimization problem until some kind of convergence criteria is met. And if we are solving the optimization problem iteratively, then we could have, this could take a lot of CPU time or CPU resources, and the computation cost may be high to solve this iteratively. So then one of the ideas of how to address this is to see what we can do with the subproblems in order to address this computation time. Now, there have been some developments in what is known as an inexact ADMM, where instead of solving this optimization problem, this potentially non-convex, non-linear optimization problem, you linearize the non-linear terms such that you end up with a quadratic problem. Right? So now you're solving an approximate optimization problem. Alternatively, what you can do is you can exploit the parametric sensitivities of the NLP that in each of these local subproblems. So the idea here is that the optimal solution between one iteration and the other is not that different, right? Because once we solve the optimization problem for a given value of x0 and lambda I, we then update x0 and lambda I, and then we go back and solve the subproblem again. And when we go back and solve the subproblem again, the only thing that has changed now is these parameters x0 and lambda I. So then if we can exploit the parametric sensitivity with respect to these parameters, then we can say, okay, once I have the optimal solution for a given value of x0 and lambda I, how will my solution change when these values change, right? So this is the idea of using the parametric sensitivities. And what we do here is, again, we use the tangential predictor. We can solve a system of linear equations at subsequent iterations instead of solving the subproblems as a full NLP at each iteration. So then once we have a solution at a given value pk for a given iterate pk, right? And the parameters here are basically x0 and lambda I, right? So once we have this solution for a given value of parameters of iteration k, we can then approximate how the solution would change at the next iteration when the parameter value is changed in these two steps, right? So that's the main idea of using the sensitivity-assisted alternating directions method of multiplying. Okay, so this is something that that we can then use to improve the computation speed. So here is a simple example where I am trying to fit a function of this form. So this is an inverse model fitting problem, and I have the parameters that are given by x1 to x6. And I have my inputs u, and I want to predict the function p. So I have about 10,000 noisy samples of the data, which I generated artificially. And I split it into 4 subproblems so that I can use, say, 4 server nodes. And what I do here is I solve the optimization problem or solve the learning problem using a full centralized approach to use as a benchmark. And then I decompose the problem into 4 subproblems and solve using the full ADMM. And I also then solve the decomposed problem using the sensitivity assisted ADMM, where I only solve the subproblems as NLPs once, and all the subsequent iterations, I solve it as using the sensitivity update. And when I compare the trained model, the predictive performance of the trained model using these 3 approaches, here I show the true value versus the predicted value by the trained model in the 3 cases. And here I see that the performance is very similar compared to when I use the full ADMM or the approximate ADMM, where I use the sensitivity update to approximate the solution of the subproblems at subsequent iterations. So here is another example. So this is a real world data from a combined cycle power plant that I took from this UCI machine learning repository. And again, here I want to decompose this into 4 data chunks and make a predictive model. So here I'm training a multi-layer perceptron. And again, here we see the predictive performance of the models that are trained using a full centralized optimization problem or a distributed learning problem that is solved using the full ADMM, and this distributed optimization problem using the sensitivity assisted ADMM. And again, we see that the predictive performance of the three models are very similar. You can also see that in the R squared number as a metric. And to point out the CPU time that we need for each iteration using the ADMM or the sensitivity assisted ADMM, we see a significant difference here. And of course, that translates to the cumulative CPU time for learning the model, right? So by using ADMM for this problem, it takes about 100 seconds using my standard MacBook. And using the sensitivity assisted ADMM, the cumulative CPU time is only 5 seconds. The same problem that I can train in 100 seconds, I can do that now in 5 seconds without degrading too much on the predictive capability of the training model. So, and also an important point to note here is that when we are making or when we're generating the trained models, it's not the accuracy of the optimization problem that's a real metric here. The real metric of interest is the predictive capability, right? So, of course, if you look at the optimal solution, if you compare the optimal solution between ADMM and the sensitivity assisted ADMM, of course, there will be some non-zero error, and that is because we are only approximating the subproblems or the subsequent iterations. But again, this does not matter in the distributed learning problem because the real metric of interest here is the predictive capability of the trained models on data that it has not seen before. Right? So that's something that I also wanted to point out. So with that, yeah, so it's so we have two paradigms that we looked at. The first is machine learning for optimization, where we wanted to use machine learning to approximate decision-making problems. And, and in order to generate the training data, I showed how we can exploit the parametric sensitivities in order to cheaply generate several data points with using only a few optimization problems that are solved offline. And in the other paradigm, which is distributed learning to train machine learning models, we can again use the sensitivity in order to improve the CPU time when using iterative methods like ADMM, where we can then use the parametric sensitivity to cheaply approximate the solution of the subproblems at each iteration. So with that, I would like to conclude my talk, and thank you for your attention, and I would be happy to answer any questions that you may have.